So this is going to be a quick overview of Chapter 5, which is log functions and exponentials. So the first thing we're going to do is look at what are our log properties. So I'll go way up here. So remember, if I have a log of two things that I'm multiplying together, I can separate those over addition. Okay, which is nice to be able to break them down, because when we start taking derivatives, the more broken down it is, the easier they are to work with. So if I have a log and I've got a division, I can separate those using subtraction. And then if I have an exponent, I can bring that exponent down front, which is really nice with our square roots and things like that, that we can kind of get rid of that function. So let's look at some. So our derivative of a natural log is 1 over x. Okay, now if I had something in here other than x, it's the derivative of 1 over that times the derivative of that. Sorry, the derivative is 1 over that, so let's do an example. So I had natural log of, say, x squared. Okay, we actually could do this two different ways. We could move that down front, so let's do that. We could say that's the same thing as 2 natural log of x. So the derivative would be 2 times 1 over x. The other thing we could do is leave it, and so it would be the derivative of this would be 1 over that times the derivative of this. Okay, which that would simplify down to the x's would cancel, so I've got 2 over x. So they really give us the same thing either way. Now, we also have logs of other bases. So say I have log a of x. From algebra, we talked about our change of base property would be, typically we're going to use natural log for everything because we know how to take the derivative of a natural log. So log base a of x is the same thing as natural log of x over natural log of a. So if I take the derivative of this, which I could even write it as 1 over natural log of a times the natural log of x. So let's say I want to take the derivative of log, let's say base 2 of x plus 3. Okay, so here I'm going to have 1 over natural log of 2 times 1 over x plus 3, and then the derivative of x plus 3, that would give me 1, this is going to give me 0, so it's just 1. So my answer would be natural log of 2 times x plus 3, 1 over that. Okay, not too bad. Let's do another one. Let's do one that's a little bit more, it's a little bigger. Okay, so let's look at this one. So first thing I'm going to do is simplify it as much as I can. So notice I've got a multiplication. So I can write that as natural log of x plus natural log of the square root of x minus 1. X squared minus 1. Now the square root here, I can write that as a 1/2 power. So I can bring that 1/2 down front. Plus 1/2. Now at this point, I could factor this to be x minus 1 and x plus 1, and it would just get, but it's, I mean, we could do that and then we'd have 3 derivatives, but we could just leave it because it's not going to save us that much time to separate it even more. So if I look at this, the natural log here will give me 1 over x. So I'm going to have 1/2. The natural log of this, or the derivative of that, is going to be x squared minus 1 times the derivative of this, which is 2x. So I'd have 1 over x. My 2's could cancel. And I had this. Now if I'd separated it to x plus 1 and x minus 1, I would have had 1/2 times 1 over x minus 1 plus 1/2 times 1 over x plus 1. It'd make it a little bigger. So really either way. Now if we're going backwards, if we're taking antiderivatives, Let's see, let's take an antiderivative of something like x squared plus 3 over x. All right, so if we're looking at this, we're thinking natural log, so we're looking at this denominator because we know, well, let me come back up here. If this is our derivative, if we're going backwards, the antiderivative of 1 over x would be the natural log of x plus c. C is not very good, plus c. So if I'm looking at this, if I can get this to be a 1 over x, or 1 over u in our case, then I could use natural log. So I'm going to rewrite this and say I'm going to let u equal x squared plus 3. So my du would be 2x dx. Okay, same thing that we did last chapter. So I'm going to use u substitution, and then notice I've got an x dx right here. I've got x dx. I don't have a 2, so I'm going to divide by the 2. I've got 1/2 du equals x dx. So now over here I have 1/2, and this is my du, this is my u. So when I take the antiderivative of this, let me scoot it up for you, it's going to be 1/2 natural log of u plus c. Now I'm going to plug back in my u, so I've got 1/2 natural log of x squared plus 3 plus c. And that would be my antiderivative. Okay, so almost any time I have a fraction, I'm going to see, can I reduce it? So I try to simplify it. If the exponent is bigger on top than it is on bottom, I may try to divide it and see if that would simplify it down. But a lot of times, especially if that exponent is bigger on bottom, this is one kind of nice little trick we have of using natural log. Okay, so let's talk about exponentials. So what if I have, I'm just going to use the back of that paper. Let's look at our exponents. So say I have y equals e to the x. If I take the derivative of e to the x, those are really, really easy. Because the derivative of e to the x is still e to the x. Okay? So that means the antiderivative of e to the x would still be e to the x plus c. Okay? Now, if I had, so say I had, e to the x squared. Okay, we're going to use the same. We're going to use that chain rule just like we did with natural logs. If I take the derivative of this, it's exactly the way it is, times the derivative of that exponent. So the derivative of x squared would be 2x, so I'd have 2x e to the x squared. Okay, so we always have to use that chain rule when we're taking our derivatives. So what if I'm going to, let's do this one, and use our product rule. So here, if I take the derivative, I'm going to have the first one times the derivative of the second, which is still just e to the x, plus the second one times the derivative of the first, which would be 3x squared. And I could simplify that a little bit. Let's see. So x cubed. Just rewrite it for a second. If we wanted to factor stuff out, we could say it's x squared, e to the x, and then x plus 3. So these would be the same. If we wanted to write it that way, if we wanted to write it this way or this way, I'm factually fine with any of them. This looks a little better than that one, though. So what if I had something that wasn't just e to the x? Similar to our logs with a different base. Say I have 9 to the x. Now, using our, we've got a rule for this as well. I can rewrite this as e to the natural log of 9. Okay, notice these would cancel. E and natural log cancel times x. Okay, so these would cancel and leave me 9 to the x. So we're going to use the same rule that we used up here. So if I took the derivative of this, I would have this piece exactly the way it is times the derivative of this up here. So the derivative of natural log of 9 times x would be the natural log of 9. Now again, this thing is the same as that one, so I'm going to rewrite it as 9 to the x times the natural log of 9. Okay. Now again, if we're going to take the antiderivative of 9 to the x, the derivative we would multiply, so the antiderivative we would divide. Okay, So it's very simply just that. So those are two rules that we use quite a bit, but they're kind of nice. So let's look at another example. So what if I had, let's even do this one. So natural log 1 plus e to the x. So say I have this, I take the derivative of natural log, we always say 1 over whatever I have here, times the derivative of the inside piece. Well, the derivative of 1 is 0. The derivative of e to the x is e to the x. So that would be my answer. So if I could simplify, that's e to the x over x plus 1. Now, if we're thinking going backwards, let's do one similar to it. Let's say e to the 2x. Okay, it looks almost identical to that. Just a little bit different. So we think the antiderivative is going to look something like this. Oh, you can't see it. So we're going to use substitution again. So I'm going to let u equal that bottom. So a lot of times we're going to let u equal our inside function, or in this case, our denominator. Those are kind of two tricks. So either look at the inside function. If there's not an inside function, we look at the denominator. If there's not a denominator, then we kind of look to see, well, if our two things multiply together, that maybe one is the derivative of the other. Those are some different kind of tricks that we're looking for. So here, the derivative of 1 again is 0. The derivative of this would be itself times the derivative of 2x would be 2 dx. Now notice I have my e to the x 2x dx. The only thing I have extra is that 2 again, so I'm going to divide by my 2. So this is 1/2 du. So I have 1/2. This is my du. The bottom is my u. So again, this is a natural log. So I have 1/2 natural log of u plus c. And we always throw it in absolute values because you can't take the natural log of something that's negative. So that just kind of saves us a little bit. So it's 1 plus e to the 2x plus c. All right. Now what if I wanted to know, let's do another one. Let's do this one. So let's say I've got e. So this one's a little different. Okay, and you all love trig functions. So let's give you some trig functions. So I'm thinking u substitution again. So what would my inside function be? It would have to be this piece up here. Okay, so if I let u equal secant of 2x, what's the derivative of secant? So if we remember back from chapter, 3, 4? It's chapter 4. Now our derivatives, we're back to chapter 2. The derivative of secant is secant tangent. So I've got secant of 2x, tangent of 2x, times the derivative of 2x would be 2 dx. We like 2's. That's a multiplication, not a subtraction. Okay, so again, I've got an extra 2 because I've got secant of 2x, tangent of 2x dx. So secant of 2x, tangent of 2x, times 2 dx. So we're going to have a 1/2 secant of 2x, tangent of 2x dx. So I've come over here. So I've got e to the u du. Okay, e to the u, and this is all du, and I've got a 1/2 in front. Now notice I've got these endpoints, so I'm going to plug those in over here. And so if x is equal to pi over 2, u is equal to secant of 2 times pi over 2. So that's going to give me pi. So secant of pi, let me think. Secant is 1 over cosine. So cosine of pi is going to give me -1. So 1 over -1 is going to be -1. So I'm going to come over here and replace that with a -1. Now let's do the same thing with our pi over 3. So I've got secant of 2 times pi over 3. So 2 pi over 3, cosine of 2 pi over 3, think our unit circle, is going to be -1/2. Okay, it's in the second quadrant, so cosine's negative. So if I say 1 over -1/2, that's a -2. Okay, so this is -2. So now we know our antiderivative of e to the x is just e to the x. So I've got e to the u. E to the u. Since I've already substituted in my endpoints, I can just plug those in. So my answer would be 1/2. I've got e to the negative 1 minus e to the negative 2, and that's my answer. Okay? So now, let's see. What if I was looking at a tangent line approximation? So let's kind of go back to that. So tangent line, so say I've got y equals, we'll do natural log. No, let's not. Let's do y equals log. Let's do one that's a different base. And I'm looking at the 0.34. All right, so if a tangent line approximation, remember we're using our equation, y minus y1 equals our slope, x minus x1. We have our x1 and our y1, have an x and y, those are just variables. We need our slope. So slope is the derivative at that point. So we need to take our derivative. So I'm going to have 1 over natural log of 2 times 1 over 5x plus 1 times 5, because 5 is the derivative of 5x plus 1. So now, let's clean that up a little bit. Well, there's not much cleaning we can do. Okay, that's not a whole lot better. So if I plug in a 3, if I plug in a 3 for x here, that's going to give me 15 plus 1 is 16. So if x is 3, my slope is going to be 5 over natural log of 2 times 16. Okay, so now I'm just going to write my equation. So it'd be y minus 4. I'm going to have leave, I don't have a calculator on hand, so we're just going to leave it like this. X minus 3. If I wanted to plug that into a calculator, I could actually get a decimal. But I'm just going to leave it, so it's not a big deal. So that would be my slope line, that'd be my tangent line approximation. Okay, the last thing in this chapter we talked about was inverses. So remember, there's two things we talked about. One was being monotonic. Monotonic means that that your function is always increasing or decreasing. The nice thing about it being monotonic is if a function is monotonic, that means its inverse is also a function. So because if your function decreases and increases, its inverse would look like this. That's not a function. So that's not a function. So we want it to either increase all the way or decrease all the way. So remember back when we talked about increasing and decreasing, if our first derivative is always positive, the function is always increasing. If our first derivative is always negative, the function is always decreasing. So what we're going to do is look at our derivative over an endpoint. We're going to look at the derivative of this function over this interval. Okay, so let's take our derivative. I'm going to go ahead and rewrite that with a negative exponent so I don't have to use my quotient rule. So now my derivative, I'd bring down my negative 2 and subtract 1, so it's going to give me negative 3. So I've got negative 8 over x cubed. Now if I look at this, for this interval, if I plug in any positive number into here, this is going to be positive. So a negative divided by a positive is always negative. So for this interval, it's always decreasing. So it is monotonic. Now, if I plugged in a negative number, notice this would be negative. So negative divided by negative would be positive. So if it's less than 0, it's increasing. If it's greater than 0, it's decreasing. So the function as a whole is not monotonic, but on this interval, it is. Okay? So that's pretty simply all you'd have to do is find the first derivative, look at the values. Basically, is there any place that's going to equal 0 in the interval you're looking at, or any place that's going to change from negative to positive? If not, then it's monotonic. Okay, the last thing is if we want to find the slope of the inverse, we don't necessarily have to find the function inverse to find the slope. So our slope is our derivative. So we'd write our inverse as f to the negative 1. Slope at some point. Okay, our formula says if I can find the derivative of my original function and then plug in the function value of my inverse, then I've got my slope. Okay, so it's 1 over the derivative, just plug in our function value. Okay, so say I have f of x equal to 5 minus 2x cubed, a equals 7. Now, notice, we kind of think back on inverses. If I have, let's see, so say I have f of x is equal to y, right? So we've got the point xy. Now, for my inverse, these actually switch places, so I'd have the point yx. So my inverse of y is equal to x. So notice this value here is an x value for my original function. So this is a y value. Okay, does that make any sense? So this a would be our y here. It's actually a y value for this one. So what we're going to do is set those equal to each other and solve for x. Okay, so that's our first step. Set these equal to each other, solve for x, because whatever this x value is here is going to be the y value for this thing here. Okay, so say I subtract 2 over, that's a cubed, that's 2, divide by 2, negative 2 is negative 1, so x is simply negative 1. Okay, so now what we're going to do is take the derivative of this, plug in this point, put 1 over it, and we're done. So my derivative is, the derivative of this is 0, bring down my 3, so it's going to give me negative 6x squared. So if I plug in my point, so I've got f, the derivative of f inverse at 7, going to be 1 over negative 6. I'm plugging in negative 1. That's the point we found at 7. My answer is 1 over 6. Okay, so it's very simply that. So always set these equal to each other, solve for x, take our derivative, plug in our point, 1 over that. All right, so that's all for chapter 5, and then we'll talk about chapter 6 in a little bit. All right.